So now to talk a little bit about text parsing and representation. So as we know, computers need to represent text as numbers, and ideally we're encoding the meaning of words and not necessarily the characters that they're made up of. So for example, we wouldn't necessarily want I saw and I cut with my saw. We wouldn't want to represent saw the same way because those are two very different meanings there in those two partial sentences. So we're also a common sort of term in text parsing is tokenization. So this is splitting text into its individual words. So just for example, if you have a sentence like drug interactions and protein interactions, that would just be splitting it into sort of a list of drug interactions and et cetera. Additionally, you might think about removing what we call stop words, which are articles and other similar words that don't necessarily contribute meaning to the text, but are repeated many times. So in that same example sentence, and would be a stop word. And then also, it's important to think about accounting for different word forms. So running versus runs, visualize versus visualization, right? So these words largely capture the same meaning. So you wouldn't necessarily want to represent them in significantly different ways. So there's two sort of main techniques that are used to deal with this word form problem. So one is lemmatization, which is where we will, so for instance, take these five forms of the word change and represent them all as change. And then we also have stemming, which is a similar sort of concept, but we'll represent these five forms of the word change as its stem, C-H-A-N-G. And in Python, these aren't things that you have to implement on your own. The natural language toolkit is quite widely used and has things like, for instance, a list of stop words, the Porter stemmer, which is sort of widely used stemming system, and the WordNet lemmatizer. And finally, we have these sort of techniques or systems that can represent words as vectors, like we said, as numbers. These are things like TF-IDF, Word2Vec, and BERT, which we'll discuss more. Quickly to talk about language modeling. So what language modeling is given a context, can we predict the probability of a next or missing word in a sentence? So in order to sort of predict that, we need to consider the history of the words in past sentences and paragraphs. And the best performing models that are kind of used currently consider words on both sides, right? Because if you think about it, the context on both sides of a word matters to its meaning. And additionally, the order of those words is also can be very important. And then the other things to consider, like we talked about previously, is things like casing and then word form with like lemmatization or stemming. And then using the Markov assumption, we can kind of say that we don't need to look at the full history of the word, so perhaps not the full paragraph before it or the full sentence even, but maybe just 2 to 5 words before. And a sort of simplistic model, language model is the n-gram model, which basically counts word neighborhoods in a corpus text and estimates probabilities. So if we look at just the simple example on the right of the slide here, we can see that our history would be these 3 words, where should we? And then the word that we're predicting would be go. And then this whole sentence is S. So the probability of S would be the probability of where times the probability of should given where times the probability of we given where should, and then finally times the probability of go given where should we. So to talk a little bit more about n-gram models, again, we're just finding the probability of a word given its occurrence near other words in the corpus. So this is using statistics to model language structure. And what n-gram really means is that we're predicting the next word from the n-1 previous words. So a bigram, for instance, would be n equals 2. So we're using the one previous word to predict the next word. And trigram would be n equals 3. So the 2 previous words to predict the next word, and so on. And to actually calculate these probabilities, we can use the Bayesian rule, where given the corpus, which is like the body of text, and a word I, we can predict the probability of word J by the number of times word I comes before word J, divided by the number of times word I is in the data set. So if we consider a simple example with a corpus made out of 3 documents, we can see, so we have document 1, learning about text mining is fun. Document 2, I want to learn more about text mining in biology. And document 3, I wish we studied more text classification. We could consider what is the probability that the word mining follows the word text. So a probability of mining given text, we can say is the count of the occurrences of text mining, which we can see occurs once in document 1 and once in document 2. So that would be 2. And then the amount of times that text appears in our corpus, which would be 3. So the probability therefore is 2/3 or 0.67. And then you can also consider what would be the probability that the word classification follows the word text. Probability of classification given text, it's the same concept. Well, we see that text classification appears once in document 3, and there's again 3 appearances of the word text. So the probability there would be 1/3 or 0.3. So in this model, if we were predicting the word after text, then we would go with the highest probability, that is mining in this case.